right?
I'm sorry.
It's whoever has the longest horns too, right?
Well,
That's
this guy was selected as a yearling.
oh, okay. So even before, I see.
He was just a little over a year old, and or maybe it's two, but he is growing, and he's growing a beautiful pair of horns. Yes.
Now, I grew up on a dairy farm, and one of the things we did when a calf was like about, I don't know, 4 weeks, 6 weeks old is get rid of the horns.
Yes. You didn't want to be horned.
No, it'd be kind of hard to get them into the stanchions for milking every day, twice a day with those horns on.
Yeah.
And that dehorning process, I think, was rather painful for them, for the calves. But you can't have those horns on if you're going to milk cows.
Is that the term polled? I've heard of polled Herefords, and I thought that was they've been dehorned.
All the cows. This is in southern Wisconsin. All the cows are dairy cows, and they're all dehorned. And so we didn't distinguish between if they'd been dehorned or not.
Well, I'd like to welcome everybody out to our first Salem Policy Seminar of the semester. Welcome Ken Judd, Senior Fellow at the Hoover Institution, and he'll be talking to us about climate change policy analysis, an example of how supercomputing can solve intractable economic models.
Yeah. Well, thank you, TJ, and thank you all for tuning in. So, this, by the way, I should point out that this represents work joint with Young Yang Kai, who was a PhD student here at Stanford in the 2000s, and now has moved on to be a professor at Ohio State University in their, I always say ag econ departments. It's probably renamed itself to Agriculture and Resource Economics, whatever, but anyway, it's in the ag econ department. And Thomas Lonchek, who is a professor now, he was a postdoc when he was doing this stuff with me, now a professor at University of Aachen. And we have written about, I think the group of us have written about 6 or 7 papers using the technology I'm going to show you to discuss a variety of issues within the whole climate change policy analysis literature. Now, I did send TJ a JPE paper that we wrote that came out in last December, which is the most comprehensive description of our model and the various details. But I'm going to describe to you here is not only what's in that paper, but also in some things that we're working on. So the fact is, I think everybody agrees on one thing: CO2 concentrations in the atmosphere are rising. Okay, that I think is uncontrovertible. And now, what should our policy response be? Well, now, of course, our policy response is going to have to be calibrated to what we think the impact of that CO2 is going to be on the economy and the climate and people. And now that's where the controversies start. But what I want to emphasize, what we emphasize in this paper, and we were certainly among the first to do this at all, and we certainly are still the only comprehensive modeling of this is ours. And what we want to know how uncertainty affects policy responses. Now, there's 2 kinds of uncertainty here. First of all, there's economic uncertainty. yes, it's a truth that is a case that the economy grows at, I forget what the acceptable number is. I'm like 1.5%, 2% a year, whatever. But that growth is certainly not deterministic. And so in terms of asking what is the impact of CO2 concentrations and temperature increases on the economy, we should keep in mind that the economy itself is growing, and it's very uncertain as to what the size of the economy will be in the future. And and this is an insight that's come out of the macro literature over the last 20 years, that the growth rate of the economy has a close to a unit root. So that means that if the economy is growing rapidly now, then it probably will continue to go rapidly for another few years. And if economic growth is low now, then it will continue to be low. Well, now what's going to happen when you think about climate, let's say 50 years from now, and the economy? It could be the case that we've had a big spurt of growth, and so then the economy is going to be very productive. On the other hand, it's likely to produce a lot of CO2. I mean, the nightmare scenario for climate people is if the Chinese and Indians all get cars and use them as intensively as we do in California and Texas. This is a nightmare scenario for CO2 concentrations with current fossil fuel technologies. And so there's an interaction between the level of CO2, economic activity, and then of course between level of CO2 and temperatures, and then the impact on economic productivity. So economic risk, by the way, is not modeled in anything. You read the Bible on this is something that whatever the IPCC puts out every few years. No mention of economic uncertainty in any serious kind of manner. And when you look at their scenarios, no mention of economic uncertainty. They talk about uncertainty in terms of the climate, and actually we do include climate uncertainty here. Because and of course a lot of uncertainty there. We don't know the laws of physics that govern weather. Now, of course, we do know the basic laws of physics, and to a very high precision. But remember, the climate is a very complex system. And of course, you have the whole chaotic theory business that if a butterfly flaps its wings in Japan, then we're going to have a hurricane in Texas. That is an exaggeration, but basically it is based on this observation that that systems like climate are very sensitive in terms of the response to initial conditions, and in fact, it ends up looking random. And in fact, that's how random number generators are produced, is by having something that's very sensitive to initial conditions. So we know the physics, but we cannot comprehend all the complexities in the climate, in weather. By the way, there is a difference between the two. I'm not going to spend a lot of time on that, but so there's a lot of uncertainty on both sides of this. Economic uncertainty and climate risk. Now, the other thing about most of this literature, they just look at your usual standard additively separable utility function. And we know that when it comes to assessing issues in terms of risk preferences, in particular, how much are people willing to sacrifice in order to reduce uncertainty, we know that people have a high risk aversion. Whereas the standard literature in climate assumes that people have a pretty low risk aversion relative to what the finance people tell us. And that's because they use these additively separable utility functions where the inverse of the risk aversion is the same as the intertemporal elasticity of substitution. Whereas what we do is we use Epstein-Zinn preferences. Epstein-Zinn preferences is what people call them. The ideas actually go back to a paper in the 1970s by Krebs and Porteous. But we are able then to represent in a better way, not perfect, but a better way, represent what people's attitudes are towards risk. And if we're going to talk about how policy should incorporate that risk or be affected by the risk, then we should incorporate realistic specifications for risk preferences.
Ken, can I jump?
Yep, sure.
Jump in on, so, I mean, you seem to be taking it as given that the Epstein-Zinn preferences are a better representation of how people feel about risk. But I mean, my interpretation of this has always been they added parameters and they got a better fit.
I believe that it's a statistically significant better fit. It's not just a matter of more parameters.
I mean,
I leave that to I leave that to you to discuss with the finance people.
I could never resolve this with
now,
Zinn.
by the way, the last point, model uncertainty. Yes, yes, they added a parameter and now they got a better fit on some dimensions. So there is a great deal of model uncertainty. And so what we do in this analysis is we take that into account. We will show you what the results are for the conventional additively separable utility functions with the conventional parameter estimates. And we will also show you what happens when we use the Epstein-Zinn preferences as estimated by macroeconomists. So my strategy always is that I'm not going to decide which macroeconomists got things right and which ones got it wrong, or empirical people in general. That's not my job, I don't think. And it certainly isn't my comparative advantage. See, my task here, I believe, is to come up with the machinery that can take the results of the best empirical work and see what that implies for policy. So I do not prejudge it to be Epstein-Zinn. I allow it to be Epstein-Zinn.
Can I ask a question? So
yeah,
when you're saying policy, I mean, I think one thing that's important for me to understand is the perspective you're taking in some sense. So
well, that'll be clear in a few minutes.
And let me just say something in terms of preferences, right? It's not the same to think about the preferences of the representative investor in the U.S. stock market than thinking about the preferences of a subsistence farmer in Kenya.
Yeah, I will. Give me a couple slides and I'll address those issues. So the thing is that this is a key theme in my research over the last 10 years or so, is that we don't know the true values of the parameters. We don't know the true models. And therefore, when our analysis should take that into account. For those of you who saw my lecture yesterday, I pointed out that the Fed in 2011, some people at the Fed, including the current president of New York City Fed, admitted that what happened is that they screwed up because they had not taken into account the uncertainty in parameters that they had estimated. So this is something that I want to do up front, not just after we screw up then say, oh, gee, we should have done this. So anyway, I don't want to get into any wars about who can estimate things correctly and all that, but my machinery can handle all these specifications. Now, the key part of climate policy, this gets the question here that we're looking at in today and in our main papers, is the social cost of carbon, which also is the optimal carbon tax. And so then what we're asking, well, we have some ideas to the social cost of carbon. And this idea is, I'm going to be referring to sort of the so-called consensus. You'll see what that is. And then ask, well, what happens if these people had thought about uncertainty? What does that do to the optimal carbon tax rate? Now, the other thing is that within this literature, there is often a discussion of the discount rate. How we have, let's say we have damages from climate change, and those damages are cash flows over time. Well, what discount rate should we use? Well, it's basic Econ 101 that once you have an economy with uncertainty in output, there is no one discount rate to use. There are multiple discount rates. Bonds, for example, are discounted at a very low rate because their returns are safe, whereas equity market returns are discounted at a higher rate because their returns are risky. And so the question here is, what discount rate should be used in analyzing the impacts of greenhouse gas policies? And what we're going to see is that it depends on the nature of the damages. Some damage processes will have damages discounted at a higher rate than others. So there is no one discount factor. Now, this is news to the people in the climate literature, where they argue over what is the right discount rate. And of course, the English, in particular Stern, loves to say that the discount rate is 0.1%, but he's talking about the social planner's discount rate, certainly nothing related to individual discount rates. So anyway, so those are the kinds of issues that we're going to be talking about in terms of social cost of carbon, and then what discount rate should we use. Now, by the way, at the Hoover Institution here, it's quite safe to argue for a currently today it would be a $40 a ton of carbon tax. Now, the reason that it's safe to do so here at Hoover is because we have George Schultz here at Hoover, who has argued that, along with his friends, Marty Feldstein was part of the group, I think also James Baker. But anyway, there are conservative Republicans. There are some people who would call these guys conservative Republicans who argue in favor of a carbon tax. Of course, the proviso they always put on it is that it has to be recycled immediately to a lump sum rebate. I disagree with that. I say, we've got bills to pay. So after you pay your bills, then play Santa Claus. But anyway, so the level of the optimal carbon tax is something that's is under discussion. Now, backing away from the climate stuff, why should economists in general be interested in this work of mine? Well, economies are also complex systems, and we have interacting economies. They're even more complex. I would argue that the international economy is more complex than the world climate. Because the thing is, the world climate, the laws of physics are the same everywhere. You can't say that about the laws of taxation, the laws of import and export, the regulations on CO2 emissions or pollution. No, the economy is much more complex than the climate. Hopefully it's not utterly chaotic like the climate is. Hopefully there's some structure we can put on it. But anyway, it's also very climate. So basically, what economists typically do is they look at extremely stylized aspects, extremely stylized models that focus on a particular aspect of an economy. And I'm always struck with the number of times people say, I have a tractable model. I have a tractable model of this or that. I appreciate the modesty that they don't say they have a good model of this or that. But of course, I thought that's what we're supposed to be interested in doing. And tractability basically means it can be done in Excel or MATLAB. Now, that definition of tractability is one I refute. That no, there are other computers in the world that you can access. And so then what we need to do is use that computing power, recognize our lack of precision in terms of knowledge about the economy and the climate, And then with that information, try to create robust and general tools that can use state-of-the-art numerical methods on modern computer architectures. Now, you might say, well, if you look at all possible parameter values, you're going to end up with nothing. You're not going to end up with any conclusions. Now, actually, about 35 years ago, I wrote a paper, came out in JPE, on the inefficiency of taxes. So I asked, what is the marginal inefficiency of labor taxation and the marginal inefficiency of capital taxation? And I found that those numbers varied enormously depending on your intertemporal elasticity substitution, depending on your elasticity of labor supply. However, what I found is that no matter what the elasticities were, the inefficiency cost of a marginal tax on capital was much greater than the inefficiency cost of increasing labor taxation. So there, we don't know what the elasticities were, but I could tell you right offhand, well, the inefficiency of capital taxation is going to be higher than the inefficiency of labor taxation. Now, by the way, and then after I wrote that paper, I then wrote another paper where I argued that in the long run, tax on capital should be zero. And now some people think that that's a very conservative kind of conclusion. I like to point out that it's also one that Lenin argued for. And by Lenin, I mean Vladimir Lenin in Revolution and the State argued that in the long run, the state would disappear and, well, the state goes and so would any capital taxation. But anyway, that's so that was a context where it turns out that even though the parameter uncertainty was very large, the qualitative implication for the appropriate direction of policy was very robust. And that's why I'm much more optimistic about doing these things than most people are. Now, here's the current state of integrated assessment modeling. That's just like you have a model where you integrate the economy and the climate. And these things are pretty bad, mostly. They typically do not have any foresight. They're just myopic expectations. They are, now most of you won't remember this because you probably might not have been born then, but when I was in graduate school in the late 70s, we wrote down dynamic models that had no foresight. We just, it was just a sequence of basically static models that then were allowed to progress over time. And they didn't, and these models that are in the climate literature don't have any uncertainty. Now the contrast, if you look at the climate models, the climate science models, these are serious models using partial differential equations to solve the transfer of heat and energy between the atmosphere and then the radiation and then the oceans. And these are very serious, very difficult numerical problems that then they use the best, most powerful computers they can. Climate scientists, the economic modelers just use their laptops and these very trivial kinds of models that mainstream economics rejected over 40 years ago. Now, even when they do something more modern, the economists in government mess up. In 2010, the Interagency Working Group of the US government came out with a report to get an estimate of the social cost of capital, social cost of carbon. And then in an early paper of ours, we showed that their numbers were off by 20 to 40%. Too high, they were too high. Now these numbers came from a program from work done by Nordhaus, who you normally don't think of as being a liberal. In fact, normally he's regarded as a conservative. But his numbers, which then the government basically copied, were 20%, 40% too high. Why? Because he didn't know how to solve ordinary differential equations. And when he wrote down the equation for heat transfer, he assumed that CO2 that was emitted 10 years from now already was warming the Earth today. So I and my friends refer to that as time traveling CO2. And this was just because he didn't know how to write down a proper finite difference system of equations to do a differential equation. And so we wrote a comment on that, and it came out in Nature Climate Change. And then some government economist wrote a response, which got about twice as much space in that journal, and is totally incoherent mathematically. But anyway, but you know, it's government work, and also the lead of that study was a MIT economist, Michael Greenstone, who was MIT at the time. So anyway, so and we believe we have the code that they wrote. So we know that they have the same flaws that Nordhaus did. So anyway, so this literature is highly flawed. Now,
And can
yes,
I push back on something a little bit? Like it almost sounds like you're judging the models on the degree of complexity and the level of computing used. I mean, shouldn't we? I mean, I understand that might be correlated with the quality, but shouldn't we be judging both of these sets of models entirely on the quality of their predictions, not the complexity of the algorithms? Like it could be a simple model.
You're right. We should judge the models by the quality of their predictions. On the other hand, the only way you know the predictions is to solve them correctly.
Fair enough.
Yeah. So and also the thing is that because because most of these people only use laptops, they have to dramatically reduce the complexity of their models. I mean, many times
because recently we've gotten kind of burned, particularly, I don't know if people have been following at the University of Texas, with people chugging, models through TAC and Stampede and doing
Ken, are you familiar with TAC that James just mentioned?
Yeah, he knows about that.
Texas Advanced Computing Center?
Yeah. TAC is a computing service there. Right?
And we've had a bunch of people running these SIR epidemiology models through our supercomputers and making really, really bad predictions. And then
by the way, Scott Atlas is a colleague of mine.
Yes.
So no, and I've seen some macro talks on this. And
so I'm a little sensitive about just because you've written down a complex model and solved.
No, but the thing is that I saw a presentation by Marty Eichenbaum last spring. And I mean, I knew from the very beginning it was nonsense.
Mm-hmm.
Because basically in the model, he assumed that as soon as you were infected, you knew it. And of course, that's one of the key features of this virus is that you don't know it when you're infected. You may never know it when you're infected. So no, the assumptions, and then of course his excuse was, well, it has to be tractable. No,
I'm just saying, I'm a little sensitive to just because they've used a lot of equations doesn't mean we should believe them.
The ability, having this computer power means you can write down models that you don't have to apologize as much for.
Mm-hmm.
And also in these papers, people write down and say, oh, we'd like to do this and that, but that's intractable. So no, and by the way, the other comment I hear from macroeconomists is that, well, we tried big models back in the 70s and that didn't work out. Well, of course not. It was big Keynesian models. And just because you make a crappy model and make it bigger and put it on a bigger computer doesn't mean that it's not crappy anymore. It's not like, oh, we lose a little money on each item, but we make up for it in volume. No, that's not the way it works.
Let me push back a little bit on what was being discussed before. So suppose we do have a more complex model, richer model, we can run it in better computers, which is all great, right? But in a sense, especially when thinking about something like climate, where we're trying to judge something that's going to be 20, 30, 50 years down the road, right? So how are we going to judge these models, right? So we can say these are rich models, so that's good, right? And potentially we can go back and use historical data to try to see how well they're predicting what's happening today or in the last 20 years. But as you say, these systems are very complex, right? And especially when you think about, I mean, and one thing you did not say, which I think is the more relevant difference between human behavior and climate, is that we don't have persistent laws of behavior. I mean, people change how they behave, how they perceive things. So there's no constant rule of behavior. So I'm not even sure how, I mean, this is a more philosophical question, but how can we actually judge a model where it's better or not? Because it could be it could be a more rough sketch of reality, but in some sense be more robust than a very complex model. And again, I'm very much for complex, detailed modeling, but I'm not sure how we can answer that question from a scientific point of view and then feel reassured that we have a better model of what's going to happen 30 years down the road.
Now, there is fundamental uncertainty, as you have pointed out. Now, what I'm saying is that when people write down models that express their assumptions, we should demand that they solve them correctly. And that's, now the thing is that, and I'll point out, as I go through this, I'll point out some places where some models where you might see they basically cheated because they wanted to make it tractable. So no, by the way, the thing is that those issues that you're talking about, those are issues, for example, that the climate science people have to deal with too. Because remember, all the climate science stuff is also out of sample.
Oh yeah, for sure. Everybody has to deal with that, unfortunately.
Yes.
Yeah.
So this is something and they have ways of dealing with it. But I find, as we'll see towards the end of the talk, I find even their ways of dealing with that to be not acceptable by economic standards. So anyway, now, Now, by the way, I'm not going to go into this, but you see, the fact is that there's a great deal of hostility to doing this kind of stuff anyway. Because I ran into some problems at Chicago where basically the other substantive person in a project was extreme green person. And when I was asked, like, are there some people at Hoover Institution that we should ask to sort of communicate? That's part of a project we can communicate with our project. I mentioned George Schultz. And her immediate reaction is, oh, we don't want to have douchebags like George Schultz communicating with us. Now, again, I look and say, okay, how many of these people know who George Schultz was? George Schultz, former Secretary of State under Reagan, Secretary of Labor and Treasury under Nixon, first head of the OMB, and most impressively, Dean of the University of Chicago Graduate School of Business in the late 60s. And this was a guy deemed to be a douchebag by a University of Chicago professor. So the atmosphere is extremely toxic. And on the other hand, you have economists that just don't want this either. You see, the battles I'm fighting are not these high-level intellectual battles that we're talking about, discussions that we're talking about here. How can we know the future 30 years? No, we're talking much more basic arguments. Anyway, now I'll talk about this as we're going to get to it. Now, I'm going to show you now the model, and then this is where I will confess to all the sins that that I've committed here. This builds on the Nordhaus model. Nordhaus has this model that he called DICE that he actually built in the early 90s and has basically the model is the same. He changes some features of it a little bit, but the basic model is the same. And so the DICE model is the model with the solid arrows. So you have the economy, which generates emissions, goes into the atmosphere. And now the CO2 in the atmosphere is going to increase the atmospheric temperatures. Now the CO2 in the atmosphere, some of it's going to diffuse into the upper ocean, and then from there, some of it's going to diffuse down to the deep ocean. And then, so this here is all of a diffusion process of the CO2. Atmosphere, upper ocean, deep ocean. And then the CO2 causes warming only in the atmosphere. But then, of course, the atmosphere is connected thermally to the ocean. And so what happens is that the ocean, when you have warming going on, the ocean will slow down warming because it's cooler. So this is the the climate part of DICE. And then what happens is that the temperature, it's only the temperature here in DICE that damages the economy in reducing output. And so that's DICE. Now then what Nordhaus did is solve for what was the social cost of carbon or the optimal carbon tax. Now, why did he have this complex climate system? Because that's what Stephen Schneider told him he should do. Stephen Schneider, he died at an early age many years ago, but in the early 90s, Nordhaus chatted with Stephen Schneider and asked Schneider for some simple basic model that represents the climate well. And this is what Schneider gave him. Now, Schneider did not give him a simpler model. It gave him this one. Now, what you find right now is that many economists, what they do is they say emissions go into the atmosphere, but that instantaneously affects temperature. Now, actually, the fact is that CO2 goes in the atmosphere and it has a half-life of about 35 years before it's absorbed into the ocean. Also, it takes time for the CO2 in the atmosphere to raise temperatures. What these economists do is they say, well, let's simplify it by saying that the CO2 goes in the atmosphere and immediately raises temperature by the long-run steady state temperature increase. And by the way, there's a paper, a lead paper in Econometrica some years ago by Golosov, Hassett, not Kevin Hassett, Krusell. Okay, it's okay. Golosov and Krusell, and then another Swedish guy who's on the Nobel Prize committee, and I forget who the fourth guy is. But this is what they did for their Econometrica paper. In order to make it tractable, they shrank this whole business down. All of this, they shrunk it down to one box. Emissions go into temperature, which then affects damages. Totally ignoring the dynamic aspects of CO2, totally ignoring the lags between CO2 and the resulting heating. And so that's, of course, going to kick up any predictions or estimation of the social cost of carbon. This is a common simplification that's done. And I don't know how you see. The thing is that what we're trying to do is look at risk issues. And now they will argue, well, this is all comes out in the long run. It doesn't matter. Yeah, well, you know, can you imagine doing finance? Let's say somebody is applying for a job in your finance department and he looks at models with 10-year time periods. Is that acceptable? No. No. You know, if you're looking at uncertainty and risk and financial kinds of things, and this is basically asset pricing is what this is. You got to go to shorter time periods. You've got to take into account the dynamics, leads, and lags. And so then for us, we have to keep that in. Others are tossing it out because it's intractable. And by the way, Krusell saw our stuff in 2012 before he wrote his stuff, where he said, for tractability reasons, we got to cut out all these things. So anyway, so that's again, a complex, I mean, a lot of economists are reducing the complexity by getting rid of this atmospheric system, which in climate is considered barely minimal, acceptable. And for the problem that I'm interested in is clearly not acceptable to shrink it down, because we're talking about asset prices, essentially asset pricing kernel. You want to have at least like an annual time period, and then things do not move instantaneously in terms of CO2 emissions and temperature over 1 year time periods. So this is how I say, okay, this is more complex, and it's justified by the fact that I'm trying to do finance. I'm trying to do things at a short time horizon, and evolutionary risk, economic risk in that. So I can't shrink the atmospheric system down to something that's only true in the long run. I can't collapse the dynamics of the atmosphere. So that's an example. Now, yeah. Now, by the way, notice I didn't put in a more complex climate thing because I wanted to stay with the base. This is a base model. Everybody knows this model. So this, if I wrote down some other model and then say, well, we want to know what happens with dice. It's not that dice is the Bible of this. It's that it's a reference point we all understand and know. And so if I say adding uncertainty is going to increase the social cost of carbon, and I do that in this common reference model, then they'll understand it a lot easier to understand than if I wrote down some big new fancy climate model and then came up with that. Now, where does uncertainty come in? Oh, by the way, where does social policy come in? Social policy is you have some efforts at mitigation to reduce the amount of CO2 that's emitted. And this mitigation is either you spend money to scrub your exhausts or put a tax on CO2 emissions, et cetera. Now, where's the uncertainty? Well, we're going to add, what we add to this framework is stochastic growth on the economy side. And also, we're going to say that the impact of atmospheric temperature rise on the damages is also stochastic. Now, in particular, the example we have in mind is that as temperatures rise, glaciers will melt. And so there is this belief that temperatures rise enough, all the glaciers will melt. And then I think you guys in Austin are safe, but I think Houston's in danger. I do know that downtown, I'm okay, but the lower parts of Palo Alto will be underwater. Also, the distance from the English Channel to Paris will be reduced by 2/3. So anyway, but now this melting process is something that is, one thing about it is that it's irreversible. If all the glaciers melt, the glaciers are never going to reform at any horizon that's of any interest to humans. So from our point of view, it's essentially irreversible. And so that's a kind of example of some damage to the economy that we worry about that does not follow a simple sort of proportionality to temperature form, but has a stochastic aspect to it. And so anyway, so that's the model. Now, notice there's only one country. Yes, I plead guilty to that. Only one country. Nordhaus has a multi-country version of DICE called RICE. R stands for regional. It was not used by the US government study group. Also, the problem with RICE is that it doesn't allow for trade. And so the international aspect of it is kind of primitive. So DICE, you should think of DICE and any of the implications as the world economy. So basically, we're assuming that everybody's catching up to the United States, and then over time we'll catch up to the United States and then follow roughly the US path of technological growth. So this doesn't, you know, this does not include, does not have any consideration here for Africa or India or China. I just watched a movie with some visitors, Crazy Rich Asians, where in Singapore, some Chinese kid is told to eat all the food on his plate because he should think of all the starving American children. Which I remember the one was the opposite, that we would say. But anyway, that's so there's a lot of economic growth going on. We abstract from this here. And so when we talk about the social cost of carbon, we're talking about as if there's a world government setting the social cost of carbon. So this is a closed economy, world economy. And that's a limitation. And I'd love to put in, there are versions of this where we have put in multiple sectors, like a forestry sector versus other parts. And I believe some work that some of my guys are doing with Buzz Brock is looking at some geographical differences by latitude. So, you know, once you do a job right, then it's easy and straightforward to do a better job on many dimensions. And that's so you talk about, we have only one good economy, one representative agent, yes, but it's all going to be done in a framework which easily allows for multiple agents and all that.
Can
Now,
I ask a question about the modeling of these stochastic damages?
Yeah.
So one thing I understand is this idea that, well, you know, the effects can be more permanent or bigger.
Yeah.
But how do you think, for example, about, I don't know, that a small change in temperature, for example, could lead the pine beetle not to die and the forest in Colorado to completely get wiped out, or you know, maybe some tropical disease spreading through, you know, temperature.
Now,
how do we think about those things that are very hard to predict, and they might be very low probability events from an example?
I mean, the thing is, by the way, that low probability events is one thing that we are very good at. Because basically we allow low probability, given the range of paths that we allow, some are low probability. So that's all done. That's all with straightforward done in this. Now, Young Yang is working with Tom Hertel at Purdue and some of his students on applying this model to forestry problems. Forestry and agriculture. Now, I don't think they've looked at the bug issues, but they are talking about how they are looking at a regional model where temperature may rise and that affects productivity of forestry, and so that some of that productivity impact could be from beetles or whatever. So now the other thing is that you would have to think in terms of, now that's not permanent because trees can grow back. However, it does proceed at a slower time scale. And so perhaps you may not want to do the annual thing. Maybe perhaps you do a 5-year time period. The framework here is very flexible. So yes, that is something that's well within. And by the way, I say that it's in our application, it's irreversible. Basically, the application, it's a Markov chain. And so you have various states of sea level rise, or you get various states of how much disease are in forests. And then by various, over time, that could be going down, down, down because of warming. But then if you guys have some success with pesticides or something, you could improve the health status by some control. So basically, even though the application in the JP paper was irreversible, the thing is that the machinery just says that it's a Markov process, so it could be reversed. So the machinery would allow for reversals.
So this is one thing that this has always troubled me with the Epstein-Zinn preferences, and I feel like it might be problematic in this area. Once you let these low probability events in, that it's very hard. You know, it's very hard to get what those low probabilities are. with this Epstein's in preference for early resolution of uncertainty, doesn't this give you kind of a lot of levers to tilt your, like, if I want to put
Yes.
on one
Yeah.
side, okay, so yes is the
Yes.
answer. So
Yes
can
is the
basically tilt
answer.
this to tell you whatever policy you want.
Now the thing is this, that there are some people, now, for example, Weitzman had some papers about stock market and low probability events, and then also climate papers, low probability events. Now, and there's others who have talked about low probability events. What I don't like about their models is that basically they're talking about events that have practically infinite cost, and the probability is practically zero.
Mm-hmm.
And so, I mean, so they with that extreme formulation, you get nice, simple little formulas and all that nice. But I think that's an extreme case. And so when I say low probability events, I don't mean things that are practically zero. And when I say high cost, I don't mean practically infinite. But even with the kinds of events that we're talking about in this paper, yes, what's going to happen is that if you have somebody with high risk aversion, which also holding fixed the other parameter, high risk aversion means desire for early resolution. Yes, what's happening is that you're going to put a lot of weight on the bad events. And this shows up in some of our results.
So if a modeler decides to write in bad events in the absence of mitigation, you get a very high tax. If you want to say, well, there's the risk that if we sort of slow down economic growth, we're going to descend into communist
Actually, the results
annihilation.
are, I'm getting ahead a bit, but I think the census comes up now. I will mention it then. The results are a bit strange because the bad event that you're really worried about is very low economic growth.
Mm-hmm.
But if there's very low economic growth, then there's also very low emission paths.
Mm-hmm.
So the damages are also low. So the implications for exposure cost of carbon can be different than you might have expected. So because bad event means a very high marginal cost, marginal utility of consumption,
Mm-hmm.
which refers is the economic growth then, and then there's this other correlation with CO2. So no, but you are right. This is a feature of the of Epstein's in preferences. Now, some people will argue that a lot of individuals are extremely risk averse. So, you know, and by looking at their portfolio behavior. Now, I know in Texas, where you have this tradition of wildcatters in the oil industry, you don't think in terms of risk averse investors. I mean, those guys are just crazy risk lovers. But anyway, but when you look at the portfolio behavior of the average coward, anyway, they do look very risk averse.
But then it gives you a lot of levers as the modeler to decide where the big risks live. That's what I worry.
I don't think of it as giving me leverage as a modeler. I just say, oh, the macroeconomists say that they love this Epstein's in stuff, so I'll add it in and see where that leaves us.
Mm-hmm.
Now, you see, I'm some people who may have particular policy objectives in mind, that may give them leverage. And by the way, everybody here at Hoover knows this, and TJ knows this, but despite all of my writings on how tax on capital should be zero in the long run, I'm a lifelong registered Democrat. So anyway, so, but I don't have a but you can't tell it in my writings. I don't have an agenda. And so, but people with agendas, yeah, you give them more levers and they're gonna have more fun. So anyway, this is the outline of the model. Now, the next slides have the differential equations and a variety of details, but I don't think you want to spend time going through those right now. So basically, you've seen the you've seen the substance, and the math is something you can. By the way, I did send these slides along with a copy of the JPE paper to TJ. Now, economic policy evaluations. Now, we did use Epstein-Zinn preferences, recursive utility. Now, of course, if gamma equals the inverse of psi, if gamma equals the inverse of psi, then you have additively separable preferences. Or if you have no uncertainty, the gamma risk aversion parameter falls out, collapses. It doesn't do anything. So that's to give you some connection with your normal additively separable utility function. This is we're going to solve out for the social planners problem. This follows Nordhaus. And so this is a 9-dimensional stochastic dynamic programming problem. Now, so at each period of time, you choose consumption. This is aggregate consumption. Also, there's population growth here and technological progress and all that, as well as, let's say, there's a productivity shock around the trend line of productivity. So you have utility over consumption, and labor. Labor is supplied inelastically, and so the Bellman equation is a value. Okay, the state variable consists of 9 things: the current capital stock, the current vector of CO2. Block M is the vector of CO2 concentrations. Block T is the vector of temperatures, atmosphere and ocean. Now then, this is chi, and I always forget what this one is, xi. Chi and xi represent the stochastic growth rate. Now, what we've done is we have basically the growth rate, the economic growth rate is itself a state variable, and then it has persistence. So you end up with the growth process having two-dimensional state system. So, and then we have J, which is the health of the glaciers or whatever, or of the health of the forest. Anyway, the Markov process stuff. We have 2 control variables. One is how much you consume. The other is how much money you spend on mitigation expenditures to prevent emissions of CO2. Now, the social cost of carbon is going to be a shadow price that comes out of this. So what we'll talk about is that shadow price, which corresponds to a tax. Now we're going to
lost in equations. Where does the climate or the vector of states affected by climate affect the economy here? Where do we see that?
Good question. Oh, it's in here. Y sub t. Y sub t is output, which is affected by temperature. Go back up here. Here is gross output. You have the productivity shock and Cobb-Douglas production, and then basically output, net total output is this in absence of climate effects production function, and then it's multiplied by this function, which reduces output as a function of the temperature and as a function of the state of J. So that's where, good question. That's where the climate is. So I on that slide, I should write it as Y sub T of block T, block J, etc. Yes, that's where it affects. Now, one nice thing about this, by the way, is that the interactions between the economy and the climate are limited to just being the temperature factor. So this is, even though it's nine dimensions, the interaction between climate and the economy is limited in its complexity, which represents reality also. Now, we solve this over annual time steps over 600-year horizon. So by the way, we do 600. Now, how do we do this? Numerically, we do value function iteration for 600 periods. This is a non-stationary model because we have productivity trends in the output. We have population growth. So this is a non-stationary model. So the only thing we can do is make some approximation of the terminal value function and then go backwards for 600 periods, which we do. By the way, what we do is, okay, this is 9 dimensions. What we do is we discretize the stochastic growth process as well as the Markov chain, representing, let's say, health of the glaciers. So because approximating a 9-dimensional value function is difficult, so what we do is now we've got it down to 6 continuous dimensions. And so that for each one of the values of these variables, we have a 6-dimensional value function over KMT. Okay, so this is a dynamic programming problem. Here are some of the preference parameters that we use. This should be basically the range of macroeconomists plus this, and then Jensen and Traeger, those are a couple of climate guys, and that's what they chose. Now, by the way, okay, how do we, okay, and then we do calibration for the macro parameters. Now, the computational method is we discretize the chi, xi, and j with 91 values of zeta, xi, 19 chi, 16 j's, I think, which, by the way, 2000, that's about 28,000 discrete states. For each one of those discrete states, we have a 6-dimensional value function. We solve it backwards in time. We make a guess as to what the terminal value function is. 600 years from now, pretty much anything is going to be okay because of the discounting. By the way, this dynamic programming problem is the social planner's problem, which all his preferences are also the preferences of the representative agent. And this is a feature of Nordhaus's work, as well as most of the work of Americans, is that they basically believe that the interest rates that are displayed in the marketplace are the true intertemporal trade-offs. Now, Stern and the English, they have very different perspective. They want their social planner to have a very, very small discount rate. Actually, they probably would like 0, but of course, the present value at 0 interest at 0% rates is not easily dealt with. So they have 0.1%. But now, what I don't like about the Stern approach is that we know that people don't discount at such a low rate. So if you're talking the social planner, in order for the social planner to impose that discount rate on society, it has to not only use that rate in deciding emissions, CO2 emissions, but also in terms of savings and every other investment. So there has to be taxes all over the place to distort things so people behave as if they have a 0.1% discounting. And I like to say, well, you know, Stalin also had a very, very low discount rate because basically he was willing to sacrifice the current generation in order to create a communist utopia in the long run. So I'm not a big fan of low discount rates because I think people often just don't understand the implications of that. So the English literature that takes this moral approach by having this low discount factor, they ignore all the implications. Whereas the American approach, typified by Nordhaus, takes the American view that, okay, people discount, the social planner should discount things at the same rate that people. So yeah, so we do this. Now, by the way, it's value function iteration, but what I point out is that this is nothing more than a difference equation in Banach spaces. You have a guess for the value function at t plus 1, or you've computed the value function at t plus 1. You then hit it with all sorts of mathematical operations, and you get the value function at time t, and you just continue to do that. This could be done. You could do new Keynesian models this way also. You could do anything in economics. I could have robust preferences and do this. It's all backwards induction by value function iteration. So the machinery that we have is set up and organized so that we could put in other utility specifications and it still runs. So now, numerical dynamic programming. Well, I think given the time, I will just say, look, our capital stock in year 21 and 200 years from now, because of the long run, the uncertainty about long run growth, if we have a lot of bad luck, we have a low capital stock in 200 years. A lot of good luck, it's high capital stock. The range in capital stock over the next 200 years is like 100 to 1. So when we write down our value function, we have to write that value function down so it models the value function over a range of 100 to 1. That's a big range for any sort of growth model, any model like this. And so we're going to have a very flexible function. Now, we have to, what we do is we pick, we pick a lot of approximation nodes and then do things at those nodes problems. So we have the approximation scheme has 1.5 billion approximation nodes. This dynamic programming, notice a nice thing about dynamic programming is that given your state, you then have an optimization problem. And since we have a lot of little independent states that we're doing this optimization problem, we can do them in parallel. And so we did this in parallel. And so we solved, for the biggest example in the paper, we solved 372 billion optimization problems. And when I saw that number, I was tempted. I said, oh, no. Should I change that model a little bit so that it uses 1 trillion optimization problems? I thought no, because by that time, Young Yang would probably see through that all I really cared about is being able to say I had 1 trillion optimization problems in one example. Now, the many examples in the paper, so there were really trillions of problems that were solved. But this one problem where we have both kinds of uncertainty was the most demanding one. And if we had just used our laptop, it would have taken 77 years. Now, both Young Yang and Thomas were postdocs at the time, and they were hoping to get jobs and then get tenure. So the 77-year time horizon was just, not acceptable to them. Actually, not for me either. We parallelized it. We got on the Blue Waters machine. We used 84,000 cores and solved it in 8 hours. Now, this is the kind of thing that should get people interested in using supercomputers. Now, by the way, the comment about made about all the models from the virus models. I once, when we were working on this, we interacted a bit with some supercomputer guy, and he was actually quite impressed with the organization of our code, because he's used to dealing with people who are basically the protein folders, you know, trying to find the minimal energy configuration of a bunch of protein components of a protein. And he said, these people don't know how to write codes. They just write down these extremely inefficient Monte Carlo simulations. And then I go in there, and the first thing I do is make it 100 times faster just by getting rid of stupid code things that they do. And he couldn't find stupid code things in hours. So yes, a lot of people using supercomputers abuse them. I mean, they say, okay, I got this big computer now. I all sorts of power. I don't have to think. But no, we did some thinking, and I guess more than some users do. And also, by the way, we ran this at about 10% efficiency. So the floating point operations were about 10% of the peak floating point operations for this machine, which supercomputer experts tell me is very good. You're never going to get 100%. I mean, those timings that you see that they brag about to get to be top 500 supercomputer, that's a very, very particular program that is used, and all their codes are highly fine-tuned for that. So running at 10% peak is as good as you can expect. So this was what we weren't just some idiots that just said, let's have the computer do the same thing a billion times, or 372 billion times.
Can I ask a question?
Yeah, sure.
So I understand the computational aspect of this, but how do these results compare to the results found in perhaps simpler models in the literature? Like, how do the final welfare actually compare?
Hold on that.
Like, if I could solve one optimization problem, I think I'd rather do that than 372 billion to get the same answer.
We'll see the payoff.
Okay.
Yeah, now, but before I tell you what the results are, I should also give you reasons to believe the results. Because, okay, we do 300, okay, if an economist tells you that they did 372 billion optimization problems to come up with their estimate of something, how much confidence would you have in their results? I have none, but anyway. And by the way, there's all sorts of papers written about how, you know, a third of all papers can't be replicated. Now, and this is when they only have to solve one equation. So what we do is we follow verification. Verification is sort of a discipline in modern computational engineering. What you do is, I love to use the phrase that Ronald Reagan always used: trust but verify. And he would always use that in these nuclear negotiations with Gorbachev, which would always piss off Gorbachev because it's a Russian saying. And of course, we all know the real meaning is trust but verify really means don't trust, I want to verify. Someday I've got to learn how to say that in Russian. But anyway. So this is the attitude I have for any numerical work in economics, including my own. I don't trust it until I can verify it. What is verification? What you do is some test of the results that is independent of the process that gave you those results. So now here in this value function iteration, I have these value functions at each iteration, and basically they're done by solving the Bellman equation at a finite number of points at each iteration. So what do? I look at some states that weren't used in constructing new value functions, and I ask, how well did the value function that I computed do in terms of predicting what the value function is at some states that weren't used in computation. You see, basically this is kind of like what do you call this? I mean, you have a sample and you break it up into two pieces, and you estimate on one, and then you use the second one to cross-validate. Now, you see, if you're doing empirical work, Mother Nature only gives you a finite number of data points, and most of them are crap anyway. But then you have to like divvy up your data points and use some for estimation and some for cross-validation. We don't have that problem. We can compute as many points as we want on this value function. So what we do is we use a finite number of points and a finite number of Bellman equations to compute the new value function, and then we generate some other states, look at other states, and see how well our value function that we computed did in terms of predicting their value. And the errors that we have in the L1 norm are at least 3 digits. And then like for the first half of the century, it's like 4 or 5 digits. The L infinity norm, so this is the maximum, the worst case, is also like 2 or 3 digits. So we have, this is a verification test now, like all sorts of diagnostics. It maybe something could sneak through, but this is hard to sneak through. And so this is what any computation in economics should do. Any macro model, any climate model, verify, trust, but then verify. Now, getting back to how much this matters. Here's the social cost of carbon results. And what we find is that this is, for this intertemporal elasticity of substitution, on using the deterministic growth, we find that the social cost of capital, the social cost of carbon is like $110 if you have intertemporal elasticity of substitution of 1/2 and of 2, and 1/2 it's $37. This basically is a range of numbers that you see in the Nordhaus models, and I think the IWG model is something like about $40. Now, as we add risk aversion and uncertainty, so here's the possible risk aversions, and then with the uncertainty that we calibrated, we see that risk aversion may increase the social cost of carbon, or it may decrease it. And what's happening here in the decrease case is that this is where the bad events are low growth. And so the thing is, you're not worried so much about the carbon concentration in the long run, so you don't put a big tax on it. It's that you're so pessimistic, and that dominates things. Here with this elasticity of substitution of a 2, you do care more about these wide range of events, and so you have a higher number. So basically, the bottom line here is that your risk preferences do affect the results, and now the most favored results in the literature, like Nordhaus and IWG, would use this parameterization. And then for their parameterization, including uncertainty and risk aversion, does increase the social cost of carbon.
Can I ask a question?
Yeah.
So, I get that this computationally comes out of, the model that you put the numbers into. And kind of the earlier conversation was a little bit about, how do we know, or how do we judge that it's the right model? It seems like there's, a big kind of model uncertainty question. Right.
Yeah, absolutely.
And that if we really wanted to understand the broader question, that we'd want to basically take the same approach and apply it to other models too, and kind of computationally figure
absolutely
out.
And what I'm doing here is showing that that's possible
Within the context of one model. And
what other models would you like here?
I'm not an expert in this space, but it seems like there are people who disagree about the model, and that was kind of Willie's earlier question.
But the key thing is that whatever model they're going to write down, it's going to look a lot like this if you're doing a social planning problem, and even if you're doing more of a macro style model, it's going to look a lot like this. It's going to be a difference equation in a Banach space.
Okay, it sounds like maybe I missed that, that you're saying this applies to a whole class of models.
Yes.
That are these macro style social planning models, but there may be models beyond that too.
New Keyn, this actually, let me see. We did some New Keynesian thing in another paper. Okay, not quite this, but no, this you see, this Paul Samuelson got a Nobel Prize because he was able to show that when you thought about things mathematically, many different problems in economics turned out to be the same thing. And when you wrote down mathematically, you just realized that they were the same thing. It's just, different letters, different, the different letters meant different things in different contexts. And one thing, okay, I'm no Paul Samuelson, but I find I have to repeat this point, that when it comes to this computational stuff, if you think about it correctly, there's not that many different problems in economics. And so this is why when I was working with Young-Yang Kai to set this up, I don't know if I even told him this. I just said dynamic programming, but always in the back of my mind is, okay, this is a difference equation in the Banach space. This is what we're doing. And so, so if we can do this with Epstein-Zinn, it's easier to do it with additively separable preferences. Also, by the way, multiple sectors are also easy to add here. Anyway, I have other papers with other people where we solved macro models with 200 state variables, and that was even on my desktop machine. So no, the scale of, we can solve large models, we can solve many different models if you get off the laptops. And this was the goal of this project that I helped create. However, after the money was secured, after the $6 million were secured, they decided they didn't need me anymore. And so cut me out. And by the way, economists also were involved in that, Lars Hansen in particular. So what you're asking me about is what I had planned on doing within the context of that project. And so the thing is, people might say, oh, Judd thinks that he can do this. Well, the thing is, that's what I was planning on doing. I delivered on a lot of what I promised. And the only reason, my funding was killed early on. So I feel justified in saying this is what I would have done had Hansen and these guys not stolen my money. And Eddie Lazier also. So anyway, it's, by the way, I get into fights with people, but I like the fact that these are leading Republican economists, Nobel winners, so presidents of universities. So, anyway, so that's the fun part of it.
Yeah, no, I appreciate the debate part of it. I'm trying to avoid fights myself, but seem to end up in them often. I get that. I just I come at things more as an empiricist, and I'm a political economy person. So I'm not super familiar with the macro models, or
I don't know. Yeah.
Or the computational stuff, but I really like the computational stuff in general. I think it's, there's a lot of uses to it. Just on the empirical side of things, we would do something that's, like an extreme bounds analysis or something to try to bound the size of the results. And, I know a lot of computational models get at that type of kind of outcome. And just, it seems like you're within, the context of a set of models here. And if you could go beyond that, you might speak broader, but it sounds like you wanted to, and just, you don't have the capability to. So
on the empirical side, I am working with Gregor Reich, who's trying to move from Zurich to Norway, which is problematic right now. And what we're doing is we want to kill off asymptotic standard errors, and instead replace it with level sets of likelihood functions, and to improve confidence intervals. So that's a computationally intensive approach to that. So anyway, no, anyway, so yeah, okay, okay, so this social cost of carbon, the discount rate stuff is obvious. I won't now. My time. Yeah, oh,
We've got about 5 minutes, Ken.
what?
We've got about 5 minutes.
Yeah. Now, uncertainty quantification is something else that is becoming, actually, there's now journals. There's a journal on uncertainty quantification, a SciM journal. And now in economics, by the way, what you're supposed to do is, if you're doing what I'm doing here, you pick one vector of parameters. You're supposed to just pick one vector of parameters. And of course, also it's calibration. You shouldn't think about the standard errors at all. Just pick that vector of parameters and solve your model for only that case. And then declare that you have an economic insight. Now, you might think that I'm just exaggerating that this is the dominant methodology. I see you have some experience too there, yes.
Our preferred specification is this, and then we finish up.
Yes. Now, so in 2014, this paper that came out in JPE last December was rejected at JPE. The only reason given for rejecting the paper was that we did sensitivity analysis. We basically had this table in the paper. We had that table in the paper. And that was, I'm not Catholic, is it mortal sin or venal sin? Immortal sin, I guess. That meant that because we had that table in the paper, the paper got rejected. Because we should have just taken one psi and one gamma, and then let's say that turned out to be 65, and then declare that to be the number, 65. Now, it didn't matter that the range here, it's not that the numbers went from like 2 to 2,000, but no. They said you show that the social cost of carbon could be any number. Well, this was a macroeconomist, maybe hadn't experienced many other numbers, but anyway, this is not just any number there. But it got rejected at JPE because we did sensitivity analysis. Now, over the course of the following 5 years, I was able to convince JPE that was not really a good idea. Now, there was an argument about that, and so the bottom line also is that my name, I had to take my name off the paper in order to get it published, or in order to be confident that it would get published anyway, because there's some threats of retaliation if my name was left on this. So that's why the paper doesn't have my name on it as an official author, but then if you look in the footnote, they make it clear that I was an author. So, but anyway, that was what that war was about. Sensitivity analysis. Now, by the way, I have, I don't know if you guys can see this, but I have this little revolving disc of death, which is not a good idea. And so I think, and my time is almost up. The rest of the slides here, what they do is they show, They show, okay, so we did uncertainty quantification. Anyway, you have to take a look at the slides also. Hopefully we'll finish off these papers in a couple months. Basically what we show is that the climate community is all messed up when they talk about what the scenarios are, what could happen. And the fact is that, what the climate community will say is that, Okay, they have this jargon, RCP 8.5. That's a particular path for CO2. So here, this is what this broken black line is what they think the temperature is going to be over time in this century. And because they don't have uncertainty in their economic models or in their climate models, they have, it's nailed down. What we show is that the uncertainty in temperature in year 2100 is at least a degree, if not more, than what they have. And remember, this is a convex loss function. Damages are convex loss, convex function of the temperature increase. And so it's important to have the distribution of these events. And also notice that here, I have pointed out that the red line is 95% quantile. So this is 5% probability events up here. And so I've gotten the distribution here so you can see what the tails are like and all that. So that's one thing that they don't do that they should. Anyway, I'll leave it at that. And thank you for your attention.
All right, thank you, Ken. And we appreciate you coming. Appreciate your two talks.
Yeah.
Coming on Zoom.
Yeah, it's coming on Zoom. I kidded TJ when he said I was going to be giving 2 lectures. I said, boy, that's a lot of work for the dinner that I'm not going to get, Traveling to Austin sounded like a lot of fun because I know there's this restaurant where before you order your steak, they bring you a big platter of meat, saying you get to choose. Anyway, but I'll have to do that some other time.
Exactly.
So, okay.
All right. Well, thank you. Appreciate y'all for coming.
Yeah.
All right.
Yeah.
Talk to you later. Bye.
Bye-bye.